Hey guys, in today's video we're going to be talking about trigonometry. Trigonometry can be difficult, but if done right, it's pretty easy. I'll show you a couple shortcuts and ways to understand what exactly is trig in this video. Let's first start off with special triangles. So basically, special triangles are special ratios in triangles that result from angles. For example, 30, 60, 90. I will in a second prove why this is true, but for all 30, 60, 90 right triangles, they will come in the ratio x root 3, and 2x for all right triangles. I'm going to show you why this is true before I start. First of all, if I were to construct an isosceles triangle with legs 2x each, not 2x, I would construct an equilateral triangle. Then I drop a perpendicular. Because in an equilateral triangle, all angles are congruent, which means they're all 60. And we've defined this as the perpendicular. Since we have a side, we have an angle, and also we have an included side. This is congruent by HL. Therefore, this angle right here must be 30 degrees, and this angle right here also must be 30 degrees. And that also must mean that these sides are congruent by the same logic, which means you have a side here and a side here. Now let's call this B, the altitude. So now 4x squared, that's because of the Pythagorean theorem, is equal to x squared plus b squared. So 3x squared is equal to b squared. Therefore, b, by that logic, must be x root 3. And that's why the 30, 60, 90 triangle works. The next triangle I'm going to talk about is the isosceles right triangle, the 45, 45, 90 triangle. The 45, 45, 90 triangle is unique because you basically have an isosceles triangle with the legs being these. So now, if I were to call this side x, this other side would also be x. So now, if I use the Pythagorean theorem, I use x squared plus x squared. Let's call this a. It's equal to a squared. So 2x squared is equal to a squared. So it's taking the square root of both sides. You get x root 2 is equal to a. This wouldn't be plus or minus because these are dealing with lengths. So now, in all 45, 45, 90 triangles, the ratio is always x is to x root 2. So now, if we want to get more familiar with that, if I just gave you this triangle right here, which had sides 30, angles 30, 90, and 60, and I told you this is 3 root 3, what I would do here is look at this. If it matches with the 60, I would move it here, whatever is the leading coefficient to this square root. And then I would times this times 2. Because remember, always with 30, 60, 90 triangles, the side opposite to the 30, you multiply by 2. Try this one. Notice how I've flipped it. Link it in the comments. What do you get? You can verify this yourself by squaring 3 root 3 and adding it to the square of 3 squared. And you should be able to get 6 squared. So if I square that, that's 9. That's 9. And this is 9 times 3, which is 12. Not 12, 27. That's 27, not 12. 27 plus 9 is equal to 6 squared. And this indeed is a true fact, because 36 is 6 squared, which is also equal to 27 plus 9, which then ends up being 36, which is equal to 36. Now, this, I'll show you how to do this. Look at this. The 2 is opposite to the 30. So which means this is the number you'd multiply by 2. And you put a root 3 here. You can test that out yourself. Now that you understand special right triangles, I'll get into trigonometry. So first things first. Let's define sine of theta to be opposite over hypotenuse, where if we had an angle, any angle right here, this would always be opposite, and this would be hypotenuse. And this right here is called the adjacent. This does change depending on the angle, depending on where the angle is positioned. So now if I were to take the cosine of this same angle, this is adjacent over hypotenuse, which means this side over this side. And the tangent of that angle is always opposite over adjacent. A way you can remember it is so, ka, toa. Sine opposite over hypotenuse. Cosine adjacent over hypotenuse. Tangent opposite over adjacent. So now if I wanted to actually apply this, let's say I had an angle theta that opens up to a 4 and a 5. Let's first find cosine of 4 over 5. Sine of theta, not 4 over 5. That would be the answer, because it's opposite over hypotenuse. However, though, if I had the theta up here and I had 4 and 5, the sine is indeterminable without using further techniques. However, though, the cosine is determinable, because look, you have an adjacent and you have a hypotenuse. So it also is 4 over 5. What do we also know about right triangles? That this angle plus this angle always adds to 90. So therefore, cosine of theta is equal to sine 90 minus theta. And sine of theta is always cosine 90 minus theta in right triangles. If I wanted to find the tangent of this angle, this angle right here, if I wanted to find the tangent, you would take opposite over adjacent. But now you're asking, what is this angle? And that's where I'm going to introduce the inverse All of these have their inverses. If you're given the sides, you can find what angle makes the side using arc sine, arc cosine, and arc tangent. And for that, you'll need a calculator. So basically, what you're gonna do, if you wanted to find the angle, sine theta, in this one, you would take the arc sine, or sine to the -1 is what it's written on most calculators, of this answer right here. What angle produces a sine of that? That's where you press second sine, 4/5. And make sure you're in degree mode. And this is around 53.13 degrees. You can test that. If I put in sine of 53.13, I should get something around 0.8. And you see that? It gets pretty close to 0.8. That's because I left out a few decimal places. So in summary, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And our special triangles, our 30, 60, 90, are always in the ratio of x root 3, 2x. The hypotenuse is always opposite to the right angle. And also, the 45, 45, 90 triangle is always in the ratio x root 2. For all 45, 45, 90 triangles. Thank you.